SwayamPrabha. Digital India. Educated India.
In lecture 4 of this course, we look at generation of aerodynamic forces and moments on an aircraft. Let us see what concepts we would like to cover here. We would look at forces acting on an aircraft in steady level flight. We would look at the genesis of the different forces: weight, lift, thrust and drag. The factors which influence lift force, which is a very important issue in aerodynamics. The factors namely flow turning, angle of attack, flow velocity, lifting area, density, etc. We would look at pressure and shear stress distribution on airfoil and consequent axial and normal forces which are created. We would also have a pitching moment created as a consequence, angle of attack, lift and drag force, pitching moment acting on an airfoil section, and a little bit on thrust equation. The key points of this lecture are lift, drag, thrust and weight, which are all different types of forces which act on an aircraft. Resultant force and pitching moment, axial and normal force, angle of attack, lift and drag forces, pressure and shear stress. Now, we will begin the discussion by looking at a typical modern passenger aircraft, a sketch of such an aircraft, where we find that it has a portion called as fuselage, which extends right from the cockpit to the tail of the aircraft, and this is the zone within which the passengers are seated, the luggage, the goods are located. Most of the air conditioning system and other mechanisms are located. Additionally, there are two wings which are fitted to this long slender structure, which we are calling as fuselage. We have a left wing and a right wing, and usually on these wings we have the engines which are mounted. There are different kinds of engines which you can think of. They could be propeller engines, they could be jet engines. Here we have a typical jet engine being shown in the sketch. Towards the trailing part of the aircraft, you have a vertical tail and you have a horizontal tail. So, these are the main elements of the aircraft structurally, and then you can imagine that when the aircraft is in the airport, it is on the ground. You need to run the engines to the desired settings, so that you can create a thrust force which will propel the aircraft forward. It will run down the runway and then gather enough momentum so that it can lift off and begin its flight. It climbs to a fairly large altitude. Typically, most of these passenger aircrafts may be flying at an altitude around 10 to 11 kilometers. And then when they are cruising, you find that there are primarily 4 forces which are acting on the aircraft, and they work in pairs. You have the weight of the aircraft, which is obvious because it has a large structure, it has a large number of passengers who are boarding the aircraft, there is a large amount of goods, a lot of fuel which is primarily stored in the wings, aviation fuel, to run the engines for long durations. So, that essentially accounts for the weight, and then in order to keep the aircraft in equilibrium along that direction, you need to generate an equal but opposite lift force, and the wings are primarily responsible for generating the lift force. So, they essentially keep the aircraft flying. Now, how is the lift created at all? If the aircraft was kept on the runway and if the engines were not running, then no lift force would be created at all. That means, this lift force is created only when the aircraft is moving at a fairly large velocity. So, there is an airflow which is coming towards the aircraft because of the relative motion, let us say at some velocity v, and because of the presence of that flow velocity, the lift is generated, which is not possible when the aircraft is standing still on the ground, which means that as the engines were throttled, as you ran the engine at a very high RPM, what it essentially did was it created a large thrust which accelerated the aircraft as it ran down the runway. As the thrust kept going, it resulted in large enough acceleration of the aircraft such that a large enough lift was created which was sufficient for the takeoff. As you speed up the aircraft more and more, what happens is that you have to keep balancing the forces all the time, so that you maintain equilibrium, and you are looking at them when it is in so called steady level flight. That means, it is not climbing anymore, nor is it losing altitude. That means, these forces are exactly balancing each other. So, we looked at the forces, let us say along the y direction. Now, what are the forces along the orthogonal direction if we call this x? So, we have 2 forces here, thrust and drag. We already saw that because we are running the engine, we are generating the thrust which keeps the aircraft moving forward. Now, there is an equal but opposite force which is the drag, which is acting exactly in the other direction, and these forces are balancing each other. Now, whatever we have discussed up to this point, if you try to review Newton's laws of motion one by one, you see that it would fit in somewhere or the other. So, an object at rest remains at rest. It is a situation like this. An object in motion remains in motion at constant speed and in a straight line unless acted on by an unbalanced force. You have a balance of forces here, and therefore, the object continues to fly at a constant speed. So, the Newton's first law applies to this situation as we explained. The acceleration of an object depends on the mass of the object and the amount of force applied by the equation F equal to mass times acceleration. So, if you look at the aircraft as a system, it has a large mass and you have to therefore apply a large force in order to make it accelerate and achieve the kind of velocities which you are talking about over here. So, it took some time to accelerate it to the cruise velocity. and until it did, the force had to be applied to keep it acceleration, or rather accelerating. Whenever an object exerts a force on another object, the second object exerts an equal and opposite on the first. This is something that you can think about. In our case, there is a good example that this engine, if you look at the exhaust of the engine, there is a high velocity jet which is moving from the exhaust. It moves this way, and this helps you to propel the aircraft forward. You can think of other examples too. Let us look at each one of these forces in a little more detail. We revisit the weight. Weight, of course, is mass times acceleration due to gravity. The total weight of the aircraft comprises of the aircraft's empty weight, fuel, and payload, which includes passengers, luggage, etc. This is true for a passenger aircraft. You can have other kind of payload for other kind of aerospace vehicles. If it is a rocket, if it is a fighter aircraft, the payloads could be different. Coming to the most important force, lift, because until and unless you have lift generation, the aircraft would never fly at all. Most of the lift force is generated by the wings of the aircraft. If you look at an expression for the lift force, you can do it this way. You can think of a non-dimensional lift coefficient CL. This is a non-dimensional measure of lift. How do we convert this non-dimensional lift coefficient into a dimensional lift force? We multiply it further by half rho v square, which happens to be dynamic pressure, which is the pressure due to the moving medium, times the wing area. Why wing area? Because we said that the wings are primarily responsible for generation of the lift. So, this is the lift force as far as an aircraft is concerned. The lift coefficient is usually determined experimentally. So, this is the CL we are talking about, and it is a function of the shape of the wing, the flow velocity, or more appropriately Reynolds number and other factors. So, it has complex dependencies, which is not very explicit here when we just mentioned it as a coefficient, and therefore, it is best done through experiments. Many factors influence the lift that an aircraft can generate, which includes its shape and size. For example, a larger aircraft would have larger wing area. So, if you look at an aircraft when it is flying above you, you may see an aircraft like this. You may see a much larger aircraft like this. And you can clearly figure out that the smaller aircraft has so much wing area, the larger aircraft has much more, and therefore, if the larger aircraft generates L2 lift, then L1 is lower than L2. So, size matters. Velocity and inclination to flow. That means, if you are flying the aircraft at higher velocities, there will be higher amount of lift created. If the aircraft is inclined to the flow, then it can generate higher lift forces than when it is level. It also depends on how much mass of the air is flowing past the aircraft, what is its viscosity, its compressibility, and so on. Lift is incidentally directly proportional to wing surface area, which we already discussed here. Now, lift generation from a wing section or airfoil is due to the flow turning. This is a very, very important concept. So, what do we mean by flow turning? If we draw a control volume which is not so small like the ones we discussed in a differential sense while defining pressure and density and so on, this is a much larger control volume. And inside the control volume, we have a wing section or airfoil. We have defined an inlet of the section and an outlet, and we are most importantly looking at the nature of the velocity as it moves into and out of the control volume. We find that it enters perfectly horizontally, but by the time it goes out, it is turned or tilted by a certain angle, say theta. Magnitude wise, V in and V out seem to be identical, but only change occurs in the directional sense. So, that is what we mean by flow turning, and this is absolutely essential for lift generation. Now, the two dimensional section that we have here is expected to be a very efficient aerodynamic section, which produces much larger lift than drag due to its streamlined shape. Now, we can show that this airfoil section will end up generating not only lift, but also a little bit of drag, but all the time if you take a ratio of lift to drag, that should be fairly large, much larger than 1 in general. Higher turning of the flow will produce greater lift without significantly increasing the drag, and that keeps your L by D ratio high, which has a lot to do with the aerodynamic efficiency of the airfoil or the wing section on an aircraft. This feature is very important for attaining stability and control of the aircraft during different phases of its flight, because you can enable different extents of turning of the flow and thereby end up generating different lift forces, which you would need for different phases of the flight. Now, let us see a typical nature of lift coefficient. We have the lift coefficient indicated along the y axis, and we have angle of attack shown on the x axis. We had discussed earlier that an airfoil section may be facing the airflow at a certain angle. How do we define this angle? There are two very important points on the airfoil section, which we call as the leading edge and the trailing edge. So, if we imagine that there is a straight line joining these 2 points, which are at the tip of the airfoil at its leading and trailing ends, then this line would be defined as the chord line. And if we now try to see what angle that chord line makes with the approaching flow, that gives you the angle of attack. So, that is the angle we have over here, and as you can see that angle of attack can vary over a range here the angle of attack is 0 and then it increases up to a point which we call as the stall angle, and we also look at the nature in which the coefficient of lift changes as the angle of attack changes. We find that this portion is by and large linear. There is a straight line moving up. That means, as angle of attack changes, there is a proportionate increase in CL. When does that happen? When the flow is nicely oriented around the body and we say that the flow is attached. Now, as long as it remains nicely oriented around the surface, what happens is that the streamlines reach the airfoil, they move past the airfoil smoothly by remaining in contact with the surface and achieving the turning. So, you can make out that it is coming in horizontally, but by the time it leaves the airfoil, it has turned by a certain angle. So, if the average direction is like this, then you have a turning which has been created. Now, there is a point beyond which this turning does not remain any more effective. So, that is the region which we have indicated by this circle, where you see that there is ineffective flow turning due to flow separation, and that happens beyond stall angle. Now, what is happening? You find here in the small diagram that we placed that the flow is not behaving nicely on the upper side of the airfoil. It is not following the surface profile properly, but rather trying to leave that surface and go away. That is what is called as flow separation, and that happens at an angle which is called as stall angle. Now, why does it happen? As you increase the inclination of the airfoil, which is indicated through the angle of attack, there is so called adverse pressure gradient created on the upper surface of the airfoil, and when the flow is not able to encounter that, it leads to flow separation. We will discuss about the adverse pressure gradient concepts further later on. So, what we understand is that having a curved airfoil section or inclining it at an angle to the flow does not provide a guarantee of desired lift. So, you cannot keep indefinitely increase the lift just by inclining it at larger and larger angles. Neither can you achieve significant amount of lift by giving enough curvature to the airfoil section itself. So, none of them will indefinitely keep increasing your lift. So, there is a point beyond which there will be diminishing returns, there will be more penalties than benefits. So, the necessity is that the flow needs to remain attached to the airfoil surface to turn effectively. There should be no flow separation. In general, till the point it remains attached, larger angle of attack produces greater flow turning and therefore larger lift, which is true till before the stall angle is reached, and therefore you see this gradual increase with increase in angle of attack. Now, why it increases linearly will be discussed later. Coming to a more formal definition of the lift coefficient, we try to express it by dividing the lift force by a set of quantities which dimensionally matches with the lift force. That means, both are in newtons when we follow SI units. It is basically a product of dynamic pressure half rho v square times the wing planform area. Wing planform area basically means when we were looking at the aircraft flying above us, the view of the wing which we saw gives the wing planform area. Now, from this equation we can figure out that the lift force, the dimensional lift force varies with the square of the velocity. So, for example, if you are increasing the velocity and making it twice, then the lift force should become 4 times if other parameters remain the same. Lift force varies proportionately with density and wing area. Therefore, if you fly high and your density is reduced to half, then your lift will also reduce to half. If you increase the wing area twice, the lift force will also become twice. Greater angle of attack produces greater lift force for the same values of density, velocity and wing area. Now, we learnt about the point of the turning of the flow which produces effective lift generation. Now, we are looking a little deeper into what is happening exactly at different points if we move along the surface of the airfoil. And here the way we have drawn it, we have shown the third dimension. That means, if we were to extend or extrude the airfoil in the third direction, then it would essentially end up producing a wing, and then on that wing surface, if you take a elemental strip, then on that strip how is pressure and shear stress working. So, if you try to draw that small strip a little larger, then you find that pressure is acting normal. So, it is at right angle to that surface, and shear stress is acting tangential to it. So, this is how pressure and shear stress are acting on that small element. So, let us say this is ds, and the angle that you have over here is d theta, or rather say theta. So, it depends on the local surface inclination at that point. Further, the velocity is coming in and meeting the airfoil at an angle of attack alpha. Now, like you have defined it over this small elemental strip, it also can be defined at other elemental strips, so that you have a complete distribution of pressure and shear stress on the surface. If you integrate their effects over the entire airfoil surface, if it is a 2-dimensional calculation you are doing, or over the entire wing surface, if you are accounting for the strip having the third dimension, then you have the total forces and moments acting on that wing section. What you can figure out is that the pressure acting on this elemental area actually creates a force which is equal to P times ds. Similarly, the shear stress also creates a shear force. So, you can say that this is a pressure force, this is a shear force, and then they have their respective directions. If you resolve these forces along two orthogonal directions x and y, then how can you express them? So, if you have the Fp expressed like this, then you have a component along y and another component along x. So, this will be an axial component of the pressure force, this will be a normal component of the pressure force. Similarly, the shear stress can also be explained like that. The effect of the shear stress is through the shear force, which can similarly be resolved into two orthogonal components. So, this could be F p x, F p y, similarly F tau x, F tau y. Now, like you have done it for a small element here, it can be done for large number of such small elements covering the entire airfoil surface. And at each such element, these components will work out having contribution along the axial and normal directions. So, finally, you will have a summation of these forces along x, which gives you the total axial force, a summation of the forces along the normal direction, that will give you the normal force. Usually, when the airfoil is generating lift, the pressure distribution is such that you have a pressure acting on the lower surface of the airfoil, which is above the free stream static pressure, and a pressure which is lower than free stream static pressure on the upper side. What we mean by free stream is that part of the flow which is far ahead of the airfoil and not perturbed or disturbed by the presence of the airfoil. So, the static pressure of air in that region is the free stream static pressure, which is indicated by P infinity. The infinity stands for conditions far ahead. Arrows pointing out of the airfoil surface essentially act like they have a more stronger suction effect, and the arrows which are pointing towards the airfoil have a more stronger pressurizing effect or compressing effect. And therefore, because of the change between the two, you have a large force which essentially acts upwards, which is primarily responsible for the lift. Now, we were talking about a distribution of pressure and shear stress about the airfoil. If you look at the sum total effect, what it produces, we find a resultant force and a moment. The moment depends on a reference point about which we are calculating the effect of the pressure and skin friction, and the moment has to be balanced by an equal and opposite one, which in a practical aircraft configuration comes from the tail section. If you do not have a balancing moment, then that would actually keep the airfoil rotating. So, you need to keep it oriented appropriately at that angle of attack and not allow it to rotate, and therefore, you need to balance it with an opposite moment which is created from the tail section. As far as the resultant force is concerned, it has an axial component and a normal component which we talked about, which are along and normal to the chord line. You could also resolve them along and perpendicular to the flow direction. In that case, there would be drag and lift. So, the normal and axial forces, after you define them, can be suitably resolved so that you can express the lift and drag forces using these relations. For this lecture, you can refer to Fundamentals of Aerodynamics by J. D. Anderson Jr. and Fluid Mechanics by F. M. White. In this lecture, we looked at forces acting on an aircraft in steady level flight. We discussed about the genesis of weight lift, and we would discuss thrust in a later lecture. Various factors which influence the lift force, namely flow turning, angle of attack, flow velocity, lifting area, density, etc. were studied. Pressure and shear stress distribution on airfoil and consequent axial and normal force generation was discussed. Angle of attack and its effect on lift and drag force, pitching moment generation was discussed. We would take up the thrust equation for the propulsion device and drag in more detail in our subsequent lecture. Thank you.